Lab 4, Enzymes by Nick Lee and Victoria Roman. What is an enzyme? An enzyme is a catalyst that speeds up catabolic reactions. They contain an active site which allows specific substrates to attach. And enzymes are highly specific. They are often made up of proteins but can vary, which means they can either be made up of nucleic acids or lipids. The induced fit theory is when a substrate can change the shape of the active site of an enzyme in order to activate it. So as seen here in this picture of the enzyme, you have a specifically shaped active site and a specifically shaped substrate, and that allows the substrate to perfectly bind to the active site and create a catabolic reaction. The catalytic cycle. In these pictures, we see a substrate bind to an enzyme and create new products. But we'll go step by step. First, a substrate will find an enzyme and bind to its active site. Once it is bound to the active site, the substrate will either combine to make one new product or convert itself so that it will make two new products. And once it's done making its two products, it will release from the active site, and then the enzyme will go on its way to find another substrate and repeat the process. So, as seen here in the bottom picture, the ATP and glucose entering an active site of an enzyme, once they're bound, they will combine and create two new products, and as a result, you get ADP and glucose phosphate. This is the hardest part of this voiceover, activation energy. Now, what is activation energy? So, for any catabolic reaction, you need to input a certain amount of energy to get a large amount of energy. So what does this mean? You need to supply energy to go over the hill so that you can maximize energy. But this is kind of a problem because the energy you use gets converted to heat. And then when it's converted to heat, it's basically unusable energy when you have a lot of it anyway. So at the transition state, which is the highest point of the hill, which is when the substrate converts into its products, is the point. Oh, that's basically what I just said. So why is this important? An enzyme is the helper here. So what it does is that it lowers the activation energy needed to go over the hill. But what does this mean? This means that you can save more energy instead of losing it as heat, and it will speed up catabolic reactions so that more of them take place without losing all of your energy to go into one reaction going over a higher hill. So even though heat sort of is a usable energy, you really don't want to use a lot of it because you're basically going to burn up all your energy and it's going to be bad. So as seen here, the red line is a catabolic reaction without an enzyme, and the blue line is the catabolic reaction with the enzyme. So what you want is an enzyme to help in that catabolic reaction, can save more energy and increase the speed of reaction so you can make more. Finally, energy saturation. Now, what is that? This is when all enzymes in a solution have a substrate attached to its active site. So as you increase the number of substrates, the rate of reaction will not increase because you know for sure that enzymes are reacting because they have a substrate attached to the active site. But if a solution is unsaturated, then there will be enzymes without a substrate, and that will lead to an increased rate of reaction because there are free substrates and free active sites. So more reactions equals higher reaction rate. Now let's talk about inhibitors, competitive versus non-competitive. A competitive inhibitor, as seen in the picture, which is right here, this blue thing, is a somewhat equivalent to a substrate. It basically has the same shape necessarily that can fit into the enzyme's active site. So what it does is that it goes into the enzyme's active site and prevents a site from reacting, and thus the substrate will no longer be able to produce its products, and then catabolic reactions get held up, and then your enzymes are basically stuck. A non-competitive inhibitor, however, is kind of different. It binds to a point known as the allsteric point, which is not an active site, and it inhibits the substrate. What it can do is that it can alter the enzyme's active site, which can either allow substrates to come in and function, or mess up the active site and not allow substrates to enter. And what it does, it determines whether or not a substrate can be catalyzed or not. So basically, as I said before, it can either allow substrates to come in or prevent them from reacting. Environmental effects. Enzymes perform under specific environments. Most of them react in an environment temperature of 37 degrees Celsius or 98.6 degrees Fahrenheit, which is the body temperature. However, pH environments can vary because they're found all over the body, and so around the stomach would be around because of hydrochloric acid, but basic somewhere else in the body. And ionic conditions determine whether or not an enzyme will properly function. So basically, where it's located in your body, so if there's a lot of salt or something, it will disrupt the active site and stop the rate of reaction. So looking at this picture here, if I can get my pen, okay. Around this arc is 37 degrees Celsius, and that's the optimal temperature. And then as temperature increases, the enzyme function will go down dramatically because heat messes up an enzyme's activity and it denatures the enzyme, which means it can no longer hold its function.